This video is going to introduce the idea of limiting reactant, and we will end with a practice problem. So limiting reactant means that you have a reaction where you have two quantities given, one for each reactant that's in our reaction. Now here I'm talking about just two reactants. Clearly there can be reactions that involve 3 or 4 or 5 reactants. And certainly you might see something like that, but traditionally these problems are going to involve probably 2 reactant molecules, and you'll be given quantities for each one. And so the idea here is that if you look at the box on the left, you can see if you count up the number of hydrogen molecules, those are the white molecules. We add those up, we get 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H2 molecules. And there are 7 of the red molecules, the O2 molecules. And we're going to react these together to form water. And so the idea here is that one of the reactants, in this case hydrogen, is going to react completely and then run out. And we're going to run out of that reactant, and once that reactant runs out, we can't make any more product. So if you look at what's inside the box, 10 molecules of hydrogen, because of the reaction stoichiometry, 2 molecules of hydrogen react with 1 molecule of oxygen. If you have 10 molecules of hydrogen, that means that they would exactly react with 5 molecules of oxygen. But you don't have 5 molecules of oxygen, you have 7, which means that at the end of the reaction, you're going to have used up all of the hydrogen, and you're going to have 2 extra molecules of oxygen. So based on the number of molecules of hydrogen that were present initially, that's 10, because it is the limiting reactant, it limits the amount of product you can form. You can't ever form any more than 10 water molecules with only 10 molecules of hydrogen. It doesn't matter how much oxygen you have. If we have an unlimited supply of oxygen, it makes no difference. Once we have more than 5 molecules of oxygen, then that will be an excess reactant, and you can't get any more water out of it, right? Because you need hydrogen and oxygen to form water. And so what's in the box on the right would be the products that would form at the end if this reaction went all the way to completion and there were no side reactions. So in this particular example, hydrogen is the limiting reactant because it limits the amount of product that you form, and oxygen is the excess reactant because you have extra of that at the end. Now, a good example of this is anytime you have a recipe where you're making something. I mean, we do this in everyday life. You know, if you want to make a grilled cheese sandwich and your recipe for grilled cheese, which is like a reaction, involves 2 slices of bread and 1 slice of American cheese, and that makes 1 grilled cheese sandwich. We're going to leave out the butter for now. Let's just pretend that's not an issue. We're going to make it with no butter. It's not going to taste very good, but that's okay. So let's say you make a grilled cheese, that's fine. But let's say you got a whole bunch of friends coming over. You're having a Super Bowl party, you're going to make some grilled cheese sandwiches, it's going to be delicious, and you're kind of concerned that you don't have enough stuff to make all those sandwiches that you need. So let's say you have a loaf of bread and a pack of cheese. Your loaf of bread has 20 slices of bread in it, and you have 16 slices of cheese. And if we use the ratio of 2 slices of bread for 1 slice of cheese, then I think we can all agree that with these ingredients, you're only going to get 10 grilled cheese sandwiches, and that you will have 6 slices of cheese left over, and you're going to throw those in the fridge for the next time you need them. Now, in this case, the bread is the limiting reactant, and the cheese is the excess reactant. Now, and this is the same way you're going to do all of these problems, okay? You're going to figure out which reactant gives you. You're going to figure out how much product you get from one reactant, how much product you get from the second reactant, and you're going to pick the lower amount, okay? There are a lot of ways to solve limiting reactant problems, but that's probably the simplest. 20 slices of bread would give you 10 grilled cheese sandwiches. 16 slices of cheese would give you 16 grilled cheese sandwiches. But you pick the lower number because you can't make 16 grilled cheese sandwiches with only 20 slices of bread. You need 32 slices of bread to make 16 grilled cheese sandwiches. So there are a lot of ways to approach these problems, okay? And we're going to practice all of them, so no worries. Now let's say we have our reaction and we figure out that the bread is our limiting reactant and our excess reactant. One little extra added piece of information If we add more cheese, it doesn't matter because cheese is not the limiting reactant. If we haven't added any more bread, bread is still the limiting reactant and the cheese is still the excess reactant. You're still only going to make 10 sandwiches, but now you'll just have extra cheese left over. So that doesn't help. Now, on the other hand, bread, that does help. Let's say we have 30 slices of bread and 16 slices of cheese. That means we could, so the two ways to sort of approach a limiting reactant problem. If I asked you which of these was the limiting reactant, there are two ways you can answer that question. Number one, you could figure out that 30 slices of bread makes 15 sandwiches, 16 slices of cheese makes 16 sandwiches, and you pick whatever gives you the lower amount, and that's the bread, right? That's one way of answering this question. Another way to answer the question is to say, well, I have 30 slices of bread and 16 slices of cheese. How much cheese would I need to exactly use up the bread with no extra cheese, no extra bread? They're gonna react exactly. They're going to be totally consumed with no extra. If I have 30 slices of bread, that means I need 15 slices of cheese. But I have 16 slices of cheese, which is one more than I need, which means that cheese is the excess and bread is limiting. Now, if you had picked the other way and you had said, well, I have 16 slices of cheese, how much bread do I need to react with that? You would have said, well, I need 32 slices of bread to react with 16 slices of cheese. But you don't have 32 slices of bread, you only have 30. So you don't have enough. And so you would say that bread is therefore the limiting reactant. So whichever way you figure this out, you definitely should be able to come to the same conclusion every time, that bread in this case is the limiting reactant and the cheese is the excess reactant. And in this case, you're going to form 15 grilled cheese sandwiches and have one extra slice of cheese. Now, obviously, if you add more and more bread, more and more limiting reactant, eventually it will no longer be the limiting reactant and the other reactant will be limiting. So if we put in 40 slices of bread, then the cheese would all of a sudden become the limiting reactant. We would make 16 grilled cheese sandwiches and we would have 8 extra slices of bread, right? So there are a lot of different ways we can ask these questions, but it all boils down to just a ratio of supplies that you need. Which supply is going to run out? Which supply is going to be extra? Back at our example here, you need twice as many moles of hydrogen to react with just 1 mole for given moles of oxygen. So let's say you have a mole of hydrogen and, wait, let's change the numbers. Let's make it more interesting. Let's say you have a mole of oxygen and then you have 1.5 moles of hydrogen. You can't just say that oxygen is the limiting reactant because it's 1 mole, it's a smaller number, because you need twice as much hydrogen to react with the oxygen. So if you have 1 mole of oxygen, you need 2 moles of hydrogen, which means that if you have 1 mole of oxygen and 1.5 moles of hydrogen, hydrogen is the limiting reactant, right? So not only do you have to convert mass into moles, you also have to use the molar ratio to figure out how much product you would form. So this flow chart is showing you how to approach a limiting reactant problem. You can convert mass of A into moles of A, and then moles of A into moles of B. And then probably the most straightforward way of simply identifying the limiting reactant is to determine how many moles of B you need to react with the moles of A that are given. And then compare that to the moles of B that you're given, and then you figure out which one is in excess. If you have more moles of B than you need, then B is in excess. If you don't have enough B, then B is the limiting reactant. Okay, and there are other ways of doing a limiting reactant problem. Probably the most straightforward way, it wastes a little bit of effort, but it makes a lot more sense to certain people, is to simply do the calculation twice. Figure out how much product you get for A, figure out how much product you get for B, and then just simply pick the lower number. And that's always going to be the right answer. So that's another way of doing these problems, and we will practice both ways. Okay, so we have a problem. I'm going to react 10 grams of hydrogen with 10 grams of oxygen. And there's a whole series of questions all related to this problem. And one thing that you should understand is that a lot of times, and we'll talk about this as we do this problem, but a lot of times, for example, part A, identify the limiting reactant and the excess reactant. There are a lot of different ways of doing that, and you might look forward in the problem and see how many grams of excess reactant is left over, Part C, what is the maximum mass of water that can form? You could use your problem solving for B or C to answer A. And so we're going to talk about different ways of answering problem A. But you might strategize and use the way that kills two birds with one stone. Okay, so let's do this problem. And as we do part A, I'll show you different ways of answering the same question. So we have 10 grams of each reactant, and that's how you know it's a limiting reactant problem. So identification of the limiting reactant and the excess reactant, there are several methods, and this is what I was telling you about. The first way involves converting mass of hydrogen into moles of hydrogen. And then you have to ask this question: how much oxygen is required to exactly consume this mass of hydrogen, this 10 grams? So you figure out how many moles of one reactant you have, and then you figure out what mass of the other reactant is required to exactly react with this mass. So if we do that, we're going to take the moles of hydrogen that we got, we're going to look at the stoichiometry and see that it's 1 mole of oxygen is required for every 2 moles of hydrogen. This is going to convert our moles of hydrogen into moles of oxygen, so we divide by 2, and then we're going to multiply by the mass of O2 to get 79.365 grams. So that means that if we have 10 grams of hydrogen, we need 79.365 grams of oxygen to exactly consume everything so that there's no reactant left over. So you take that mass of oxygen and you compare it to what's given in the problem. What's given in the problem is 10 grams of oxygen. So what this means is that if we have 10 grams of oxygen, but we need almost 80 grams of oxygen, that means that we have less than we need. So given 10 grams of hydrogen, we would need almost 80 grams of oxygen to exactly consume that hydrogen, but we only have 10 grams of oxygen. That means that oxygen in this problem is definitely the limiting reactant because we need more than we have. So those 3 dots mean therefore limiting reactant is oxygen, which means the excess reactant is hydrogen. So that's one way of figuring it out. We could have alternatively calculated the mass of hydrogen required to exactly react with 10 grams of oxygen. So you can pick either reactant, it doesn't matter. So instead of starting with hydrogen, if we started with oxygen, that we're going to do down here at the bottom. So we have 10 grams of oxygen, and instead, this is just an alternative way of answering the same question. So you wouldn't do this in addition to what we've already done. We've already answered part A, but this is just another way of answering part A. So here we're going to take mass of oxygen, convert it into moles. Then we're going to use the stoichiometry in the problem to convert to moles of hydrogen. Then we're going to multiply by the molecular weight of H2 to determine that we need 1.26 grams of hydrogen to exactly react with 10 grams of oxygen. And then you're going to, just like before, compare the mass that you need to the mass that you have. So you need 1.26 grams, but you have 10 grams, which means you have more than you need. So that means that hydrogen in this problem must be the excess reactant. So you should get the same answer no matter which way you go. And we do, right? We determine that hydrogen is the excess reactant because we have 10 grams, but we only need 1.26 grams. So hydrogen is excess reactant, oxygen is the limiting reactant. You should get the same answer regardless of which reactant you choose. Now, a third and final way of identifying the limiting reactant is you can kill 2 birds with 1 stone here and answer part C, what is the maximum mass of water that can form? So we could answer part B, or C is very often the question that's asked, is what is the maximum mass of product that can form given these 2 masses of reactants that react together? And so often C is the only thing that's asked, or sometimes maybe A and C. So if we answer, we can go ahead and answer part C, and we can use that answer to answer part A. So we're going to do part C, and I'll show you how you use your answer to, how you use that problem to answer part A. And we can answer part B too. So we're going to answer part C using both reactant quantities. We're going to convert 10 grams of hydrogen into moles of hydrogen, and then we're going to convert that into moles of water. And the reason I'm picking water is because that's the product we're asked about. We're going to convert moles of hydrogen into moles of water, and then moles of water into grams of water. And that's one of our potential answers to part C. We're going to do the same thing using 10 grams of oxygen as the reactant mass. Convert to moles of oxygen, convert to moles of water, convert to grams of water, and then we're going to have an answer there, 11.26 grams. So we've answered the same question, part C, using both reactant quantities. And then we're going to look at our answers. And whenever you're answering a limiting reactant problem, the answer for how much product is made is always going to be the lower value, because once you've run out of the excess reactant, once you run out of the limiting reactant, you can't make any more product. And so the limiting reactant determines the amount of product. It limits the amount of product that can form, right? So you choose the lower value, 11.26 grams of water. That's the answer to part C, except we need to reduce to 3 sig figs. And whatever reactant gave you that lower amount is the limiting reactant. So we could have just done these two calculations here, choose the lower value for the answer to part C, and then whichever reactant gave you that lower value, oxygen in this case, oxygen is definitely the limiting reactant, and that means the other reactant is the excess reactant. So we need to reduce that to 3 sig figs to be the answer. It looks like 11.3 grams of water up here at the top. And the reason for that is because we started with 10.0 grams of oxygen, and that has only 3 sig figs. Stoichiometric coefficients are exact. So we need to round to the 10th place. Now we've done part A and part C. If we do part B, how much in grams excess reactant is left over? So we already did this earlier. That's what those words there said. So we did this already at the very beginning. This was one of our ways of answering part A, was to figure out how much of the other reactant is required to react with the first reactant. So we already did this, but we're going to do it again just for fun to make sure everybody understands. 10 grams of oxygen, that's my limiting reactant. If we calculate the mass of hydrogen required to exactly consume this oxygen, we're going to start with converting from grams of oxygen to moles, moles of oxygen to moles of hydrogen, and then moles of hydrogen to grams of hydrogen. This is the mass of hydrogen that will react as long as the reaction goes to completion, and then all of the oxygen will be gone because it is the limiting reactant, and then you'll have some extra hydrogen left over. So this question part B is asking, what is the mass of excess reactant left over? So you're going to take the original mass, which is 10 grams, and subtract 1.26, and that's going to give you 8.74. This is just saying, does this look familiar? We already did this calculation as part of part A. It was the second method we did out of 3 methods to answer part A. So you can see that you can just move on to part B and part C, and you can figure out the answer to part A as part of that problem solving. So significant figures here, 10.0 is accurate to the 10th place, 1.26 is accurate to the 100th place. When we subtract these two, we need to round this number to 8.7 grams. It doesn't look like I did that, but I should have. It should be 8.7. Now we're going to do part D, and we're going to calculate percent yield. Now we know the amount of product we got. 11.26 was our answer to part C. That's the theoretical yield, which is the maximum yield possible. 10.0 grams of water is what actually formed, so that is the actual yield. So percent yield is always the actual yield divided by the theoretical yield, which is the maximum possible yield, times 100. And that should give you a number that is less than or equal to 100%. I'm going to round that to 88.8%. It has 3 significant figures because 10.0 and 11.26. This is actually also rounded to 3 sig figs. I'm using the unrounded number though, but it's still only accurate to 3 sig figs, and so the answer will be 88.8%. 3 sig figs for both of those. And that's because it came from 10.0 grams, 32.00 grams per mole, 18.016. The two molecular weights have 4 sig figs.